In this lecture, we're going to talk about types of balances and degree of freedom analysis for reactors. And then we're going to apply this to equilibrium reactions. There are three types of balances that we'll use for reactors. The first is an atomic species balance. This is often the simplest, especially when you have multiple reactions. The next is a molecular species balance. This is used only for simple systems. And the last is extent of reaction. This is the preferred type of balance for equilibrium reactions. Before we perform balances on reactors, we'll do degree of freedom analysis. And in these degree of freedom analysis, we need to be able to identify independent species and independent, both molecular and atomic species, as well as independent chemical reactions. If two molecular or atomic species appear in the same ratio throughout a process, only one is independent. A situation in which they do appear in the same ratio is shown over here to the right for this process flow diagram. This input stream here is air, and in air we know the ratio of oxygen to nitrogen is 21 to 79. This output from the process contains oxygen and nitrogen in the very same ratio as in the input air. The ratio is of 21 to 79. As a result, oxygen and nitrogen cannot be counted as two independent species. Only one of them is independent. The other can be calculated from the ratio of 21, the known ratio of oxygen to nitrogen of 21 to 79. To count the number of independent chemical reactions, we must ask ourselves, can any of the chemical reactions that are present in the process, can any of them be obtained from the others by adding or subtracting them? So in this example here, we have three chemical reactions that can occur. And we have the first one, that A plus B yields C. The second is C yields D plus B. And the third is A yields D. Since the third chemical reaction can be obtained by summing the other two, then the third one is not independent. We only have two independent chemical reactions. When we sum these two, 1 and 2, what we find is that since C is a reactant in the second one and it's a product in the first, the C's will cancel. And because B is a reactant in the first and a product in the second, the B's will cancel when we add these together. That gives us this A yields D. There are three types of balances that we'll use for reactors. The first is a molecular species balance. As its name implies, it's a balance on each independent molecular species. To determine the degree of freedom, the degrees of freedom associated with a molecular species balance, we first count the number of labeled unknowns for the process flow diagram. We add to that the number of independent reactions. Then we subtract the number of independent molecular species. We also subtract the number of other equations that are available. For example, we note that a reactor is at equilibrium, or we're given the conversion of one of the chemical species. And there can be other types of equations that are given to us. If the degrees of freedom is equal to 0, then the problem is solvable. If this is a positive number, then we need one more equation in order to solve the problem. At steady state, we're going to write balances of the form that 0 is equal to what comes in of each species minus what comes out plus the generation minus the consumption of that species. A second type of balance is an atomic species balance. And as its name implies, this is a balance on each of the atomic species. So for instance, if we have methane that has carbon and hydrogen in it, it'd be a balance on the carbon atoms that come in and out of the process. It could be a balance on the hydrogen. The number of degrees of freedom associated with an atomic species balance is given by the number of labeled unknowns, from which we subtract the number of independent atomic species this time. We also subtract the number of independent or inert or non-reactive species, as well as any other equations that might come from an equilibrium specification, a conversion of one of the chemical species, or some other equation. And at steady state, our balances are going to be of the form that 0 is equal to N minus out plus generation minus consumption. And we have to realize that if we're talking about atomic species balances, that the generation consumption of an atom is 0. we're not converting a carbon atom to something else. All the carbon atoms are preserved through the process, so that for these balances on reactors, these atomic species balances on reactors, we're going to say 0 is equal to N minus out. The third type of balance that we'll use for chemical reactors is one that is based upon extensive reaction. And we do a degree of freedom analysis for balances using extent of reaction. We'll sum the labeled unknowns and the independent reactions, and then subtract the number of independent reactive species, as well as we'll subtract the independent inert or non-reactive species that are in the process. We'll also subtract other equations, such as an equilibrium specification or a conversion relationship or some other equation that we might be given. And at steady state, our balances will be of the form, as with the previous ones, that 0 is equal to N minus out plus generation minus consumption. Now, let's do an example of balances around a reactor, and in particular, balances around an equilibrium reactor. The first problem we're going to consider is the reaction to form methyl acetate. Methyl acetate is the ester of methanol and acetic acid, and it's used as a solvent in glues and nail polish removers. Here's a picture of the molecule, an atomistic drawing of it, and here's the chemical formula. If you look at the chemical formula here, this part to the left is from the acetic acid that is used in the reaction, and the part on the right is from the methanol. When acetic acid and methanol react to form the ester, a molecule of water is produced. So the description of the problem we're going to work is here. We have a gas phase reaction between methanol and acetic acid to form methyl acetate and water. The 4 species are shown here. It's an equilibrium reaction as indicated. Now here in this statement, the letter A is used to represent methanol, the letter B is used to represent acetic acid, C the methyl acetate, and D water. We're also going to use letters. We're going to use M for methanol, we're going to use A for acetic acid, we're going to use Ma for methyl acetate, and we're going to use W for water. So this reaction takes place in a batch reactor and it proceeds to equilibrium. When the mixture is at equilibrium, the ratio of the mole fractions, the product of the mole fractions given here, is equal to 4.87. So we'll take the mole fraction of the methyl acetate, multiply that by the mole fraction of water, and then divide that by the mole fraction of methanol at equilibrium and the mole fraction of acetic acid. We're going to solve this problem using extensive reaction. And from the definition of extent of reaction, we know that the amount that leaves a reactor, a batch reactor, this N sub I, is equal to the amount that enters, this N sub I0, plus or minus the stoichiometric coefficient for that reactant, times the extent of reaction. We'll use the plus in this equation here when the species is being produced, it's a product, and we'll use a minus when the species is a reactant. And the nu sub I here is the stoichiometric coefficient that we obtained from the chemical reaction that you see here. Each of the stoichiometric coefficients are 1 in this equation. It's 1 for the methanol, it's 1 for the acetic acid, as well as the methyl acetate, as well as water. Now, what I'd like for you to do is to pause this lecture and then draw and label a process flow diagram for this reactor. You'll simply draw a box, which is to represent the reactor, and one stream coming in and one stream coming out, and then label those 2 streams. So I'll give you a moment now to do that. Well, hopefully you took a moment in order to draw that process flow diagram. Well, here's what I would draw. And I've reproduced some of the information from the problem statement, that the product of the methyl acetate mole fraction in water divided by the product of the methanol and the acetic acid mole fraction is equal to 4.87. And I reproduced the equation from which we're going to calculate the number of moles that leave from the moles that enter of each species in terms of the extent of reaction. So here's our reactor, the square you see here. And below, if we go back to the previous problem statement, you'll notice that for this process as given in the problem statement. The mole fraction of methanol in the feed is 1/2, and the mole fraction of acetic acid is 1/2, and there's no other species that are present. We're not told the number of moles that are fed to the reactor, nor are we told the number of moles that leave, so we're free to take a basis. And here the basis is that the number of moles that enter, the total number of moles that enter, is equal to 1. We know nothing about what comes out of this reactor. We don't know the number of moles. We don't know the mole fraction of methanol, acetic acid, methyl acetate, or water. So the first 3 species, the methanol, is given, the mole fraction of methanol is assumed to be represented by the variable y sub 1. We're going to let y sub 2 represent the mole fraction of the acetic acid. We'll let y sub 3 represent the mole fraction of the methyl acetate. Therefore, the mole fraction of water is just 1 minus y1 minus y2 minus y3. To determine if this problem is solvable, to do a degree of freedom analysis for a problem in which we're going to do balances using the extent of reaction, we have to count the number of count the number of unknowns and independent reactions, as well as the number of independent reactive species, number of inert species, any other equations that we have. We're going to sum those all up and see to determine if it's solvable. The number of unknowns will be a plus term in the sum. The number of reactants will be another plus term, and we'll subtract off the independent reactive species. We'll subtract off the number of inert species. We'll subtract off other equations. Why don't you try counting those now? I recommend pausing the lecture in order to do this, because we're going to continue, and I'll show you the results in the next slide. Well, let's go through this step by step. Let's count the number of unknowns. If you look at the stream coming into the reactor, we assumed as a basis the total number of moles is 1, and we're told the mole fraction of methanol and acetic acid are both 1/2, and there's no other species present. So the stream is fully specified. There are no unknowns associated with it. For the stream coming out, we have 4 unknowns. We don't know the total number of moles, n sub t, so that will be in our list over here of unknowns, nor do we know y sub 1, y sub 2, or y sub 3. Therefore, we have a total of 4 unknowns. The number of independent reactions for this problem is 1. There's only 1 reaction. We'd only have to determine if all the reactions are independent if there's more than 1. The number of independent reactive species are going to be the methanol, the acetic acid, the methyl acetate, and water. It's unlikely they're going to be in the same ratio in the product as they are in the feed, so we're going to assume that they're all independent. Therefore, we have 4 reactive species, which we'll put a minus sign in front of when we do our sum. There are no inerts in the feed, so the number of inerts is 0. And we look at other equations that we have available to us. We have 1. That's the equilibrium relationship, that the product of the methyl acetate and water mole fractions divided by the product of the methanol and the acetic acid mole fractions is equal to 4.87. So this one additional equation, we'll put a minus sign in front of when we do the sum, and we sum these all up. We have a plus 4 from the unknowns, a plus 1 from the reactions. We'll subtract off the 4 independent reactive species. We have no inerts, so there will be no contribution from that. And finally, we have the 1 equilibrium relationship, and we sum this all up, we get 0. So the problem is solvable. Next, in problems like this, we're going to relate the number of moles that come out of the reactor, this n sub I, to the number of moles that enter, n sub I is 0, plus or minus the stoichiometric coefficient times the extent of reaction. And in reactor problems, we often will not only list the mole fractions below the stream arrow, we'll also list the flow rates of each, or the amounts of each of the species. And so what you see here for the feed, that we have the n sub t 0 is the total number of moles that enter into the reactor. And we've listed the mole fractions of each of the species that are going into the reactor. We're also going to list the amounts that go in below here. So an n, this lowercase n with the species name, comma 0 represents the amount that comes in. The lowercase n with a subscript species name represents the amount that comes out. We also have the mole fractions there as well. So why don't you go ahead and try to write the number of moles of methanol that comes out in terms of the extent of reaction, the number of moles of acetic acid, as well as the number of moles of water and methyl acetate. I'll pause right now for a little bit. I hope you do too, that you pause the lecture and try to write these expressions, because when we move on to the next slide, the answers will be given. Let's go through each of these. Let's start off with the number of moles of the methanol that leaves the reactor. The number of moles of methanol that leaves is equal to the number of moles that enter, N sub m comma 0. And then if we look up here at the relationship that we're going to use to determine what comes next, we have to either use a plus or a minus. A plus is if the species is a product, the minus is if it's a reactant. Methanol is a reactant, so we'll put a minus here. Next, we need to obtain the stoichiometric coefficient from methanol from the balanced chemical reaction. The coefficient is 1, so we'll have a minus 1 times xi. We'll repeat this process for each of the other species. So we look at the acetic acid, the amount that comes out, N sub A, is equal to the amount that comes in, N sub A 0. When we decide upon a plus or a minus, we note that the acetic acid is a reactant, so we use a minus. I have a minus here. The stoichiometric coefficient for acetic acid in the balanced chemical equation is 1, so I have a minus 1 times xi. Next, for the methyl acetate, the amount that comes out is equal to the amount that comes in. We'll use a plus because it's a product, and the stoichiometric coefficient is 1, so it'll be a plus 1 times xi. And same thing's true for water. The number of moles of water that comes out is equal to the number that enter plus xi. If we sum these all up, we'll get the total number of moles that come out. So if we sum up the number of moles of methanol and acetic acid, methyl acetate, and water, what we find is that we have a minus xi, which is minus 2 total xi, plus 2 xi. So the xi's all cancel when we sum these up. The total number of moles that come out, N sub T, is exactly equal to the number of moles that enter. It's a constant. It doesn't change as the reaction progresses. There's no change in the number of moles of reaction. If you look here, that we have 1 mole reacts with 1 mole to produce 1 mole and 1 mole. So 2 moles react and give us 2 moles. So we should see no change in the total number of moles due to reaction. This won't always be the case. There will be many cases in which there is a change in the number of moles. Either the number of moles will go up or the number of moles will go down. Let's take those expressions that we wrote for the number of moles that come out of each of the species, and let's plug in the known number of moles that enter. We know from our process flow diagram that the number of moles of the methanol enter is 1/2. We calculate that because we know the total number of moles that we put into the reactor is 1, and the mole fraction of methanol and acetic acid are both 1/2 in that feed. So the total number of moles of methanol enter is going to be the total 1 times the fraction 1/2 to give us 1/2. Likewise, the number of moles of acetic acid is 1/2. There's no moles of methyl acetate in the feed. This N sub Ma0 is 0. Likewise, there's no water in the feed. This N sub W0 is 0. So these expressions for the number of moles that exit reduce to, for methanol, 1/2 minus xi. We have the same relationship for acetic acid. And the number of moles of methyl acetate and the number of moles of water that are produced are both equal to xi. They're equal. Once we know the number of moles of each of the species, we can determine the total number, which we already said is 1. And from the total number and the number of moles of each species, we can calculate mole fraction. So for instance, the mole fraction of methanol is the number of moles of methanol that leaves, 1/2 minus xi, divided by the total number of moles, 1. So just 1/2 minus xi. We do the same thing for the acetic acid. We take the number of moles divided by the total to get the mole fraction. And we do the same thing for methyl acetate and water. What we find is that the mole fraction of methanol is 1/2 minus xi. We have the same expression for acetic acid, and both the mole fraction of both methyl acetate and water, those mole fractions are equal to xi. Now what we're going to do is plug these mole fractions into our equilibrium relationship here. Now I'm not going to show all the details of that. I'm going to show you the result though on the next slide. Actually, it'll be one more slide after this. We're going to substitute these expressions for the mole fractions into this equilibrium relationship. So why don't you go ahead and do that. For y sub m, plug in a half minus xi. For y sub a, half minus xi, and see what you get. You can compare that to the answer on the next slide. When you plug in the mole fractions, what we find is that xi squared divided by 1/2, 0.5 minus xi squared, is equal to 4.87. This turns out to be an equation that we can solve by simply taking the square root of both sides. So on the right-hand side, we'll have the square root of 4.87. We take the square root of the left-hand side, we end up with xi over 1/2 minus xi. And this expression can be rearranged to solve for xi, as you see here. I won't go through all the algebra here, but you can calculate that the value of xi is 0.344. In many cases, you won't be able to solve this as easily as you have here, but we have a tool to do that. We can use Solver in Excel to determine the value of xi. We'd put the value of xi in one cell, we'd calculate the equilibrium constant here, and we'd set that cell in which we calculate the equilibrium constant to a value of 4.87 by changing the value of xi. So once we know the value of xi, we can plug it in to calculate the mole fractions of each of the species, as well as the flow rate of each of the species. And that's what you see here. Next, we're going to calculate the fractional conversion of methanol and acetic acid. The fractional conversion of a species is equal to the amount of that species which reacts divided by the amount that's fed to the reactor. So let's consider the methanol to begin with. The amount that reacts is equal to the amount that's fed, 1/2, minus the amount that exits. From the expressions up here, the amount that exits is 0.156. So that difference is the amount that reacts. We'll divide that by the amount that enters to calculate the fractional conversion. We get a value of 0.688. So 68.8% of the methanol that enters reacts. To calculate the fractional conversion of the acetic acid, we have the very same expression. Because 0.5 moles of acetic acid enters, the amount that exits from the expressions up here is 0.156. We'll take that difference to calculate the moles of acetic acid that react, divide that by the moles that enter to get the fractional conversion of 0.688. Now let's work a second problem. This is a problem that will also be you'll complete for your homework assignment. I'll let you read through the problem statement here, and I would recommend that you pause the lecture and read it yourself before proceeding. So I'm going to go through the problem statement now, review it with you. Hopefully you took a moment in order to read it yourself and to think about it. This reaction that you see here, the water-gas shift reaction, is a very important one in producing alternative fuels and also trying to address greenhouse gas problems associated with CO2 emissions. I'm not going to go through the details of why, but it turns out to be a very, very important reaction in both those cases. This reaction takes place at low to moderate pressures and involves reaction of carbon monoxide, a very poisonous gas, with water to produce CO2 and hydrogen. It's an equilibrium reaction as indicated here. Also, if you look at it, you'll see that it's balanced, that one CO reacts with one water to produce one CO2 and one hydrogen. There's no change in number of moles due to reaction. So if we have 2 moles that enter and contain our reactants, we'll produce 2 moles of product. Now the equilibrium for this reaction is given approximately by the equation you see here, that we take the product of the mole fraction of CO2 and hydrogen, divide that by the product of the mole fraction of CO and water. We'll set that equal to an equilibrium constant, which depends upon temperature in this case. And that expression, the dependence on temperature, is given by the equation you see here. To calculate the equilibrium constant, we take 0.0247 and multiply by the exponential of 4020 divided by the temperature in Kelvin. Now for this problem, we're going to assume that we have a feed to a batch reactor containing 20 mole percent CO, 10% CO2, 40% water, and the balance is some inert. It might be nitrogen. And that this reaction takes place at a temperature of 1123 Kelvin. Now, what I'd like for you to do is take a moment and, assuming a basis of 1 mole of feed, draw and label a flow chart. Then carry out a degree of freedom analysis using based upon balances using extended reaction. And what you should be able to prove is that you have enough information in order to solve for the composition and flows of the product that comes out of this batch reactor. And then after that, we're going to actually do the calculations. So I want you to pause the lecture now and attempt to draw a process flow diagram, because when we move forward to the next slide, you'll see the result. Okay, just to remind you that we're going to be drawing a process flow diagram and performing a degree of freedom analysis for a batch reactor in which the water gas shift reaction occurs. So let's talk about the process flow diagram and the degree of freedom analysis based upon extent of reaction. So first of all, that equilibrium relationship is reproduced here. The product of the mole fraction of CO2 and hydrogen divided by the product of the mole fraction of CO and water is equal to this equation here, in which we have to plug in the temperature in order to calculate a specific value. So we plug in a value for the temperature of 1123 Kelvin. Here, you can see that we can calculate that the equilibrium constant is 0.886. The process flow diagram is drawn here in the lower left-hand corner. The reactor itself is simply the box. We have an input stream and an output stream. We took as a basis 1 mole total going into the reactor, and we're told the mole fraction of CO, water, and CO2 in the stream are 0.2, 0.4, and 0.1. There's no hydrogen, and the balance is an inert. So the balance of the inert mole fraction is 0.3. Always like to check and make sure that I've labeled a stream correctly in terms of mole fractions by adding them all up to see if they add up to 1. Let's check that here. So the mole fraction of CO is 0.2. We add to that 0.4 to get 0.6. 0.6 plus this is 0.7. 0.6 plus 0.1 is 0.7. 0.7 plus 0.3 is 1. So indeed, these all add up to 1. For the product that comes out, we know nothing about it. We don't know the flow or the total amount that comes out, so we'll represent by the variable n sub 1. We don't know the mole fraction of CO. We'll represent it by y1. Nor do we know the mole fraction of water. We'll use y2 to represent it. y3 will represent the unknown mole fraction of CO2. y4 will represent the unknown mole fraction of hydrogen. In the inert, we can calculate the mole fraction of it by subtracting from 1 all the other unknown mole fractions. 1 minus y1, minus y2, minus y3, minus y4. We can check and make sure that the streams labeled properly by simply adding these up. So if I add up y1 plus y2 plus y3 plus y4 plus this here, we find that they all add up to 1. Now let's do the degree of freedom analysis based on extent of reaction. First, we have to calculate the number of unknowns. There are no unknowns associated with the feed. Everything specified the amount as well as the mole fractions. We know nothing about the product though. So if we count the number of unknowns in the product, we have n sub 1, y sub 1, y sub 2, y sub 3, y sub 4. We have a total of 5. We'll put a plus sign in front of that. We sum up these values here to determine the number of degrees of freedom that we have. We calculate the number of independent reactions. There's only one reaction, so this would just be 1. We don't have to worry about determining if all the reactions are independent, so we'll have a plus 1 here. Next, let's count the number of independent reactive species. There are 4 species: carbon monoxide, water, carbon dioxide, and hydrogen. So I have a minus 4. We'll count the number of inert species. Well, we don't know the name of it, but we do know there's an inert. So we have one more. So we have 1 species. We'll put a minus 1 in front of that when we do our sum. And finally, we do have an equilibrium relationship, another equation. So one of those, and we'll put a minus 1 in front of that when we do the sum. If we sum these all up, the number of unknowns plus 5. We add to it the number of independent reactions, plus 1. Then we subtract off the independent reactive species. We're going to assume they're all independent. We have no reason to suspect that they're in the same ratio throughout the process. We'll subtract off the number of inert species, and then we'll subtract off the number of other equations or equilibrium relationship. We get 0. So the problem is solvable. Next, and this is what we're going to be doing in class as well as for the homework, I would like for you to write an equation for each reactant, for the flow of each reactant, the number of moles of each reactant, and the product from the reactor in terms of the extent of reaction, based upon the equation that we have here for doing so. And also I'd like you to write a mass balance for the inert. And for an inert in a reactor, we'll just say N is equal to out. It's not a reactant, so we don't have to worry about any consumption or generation terms. Once we have all these expressions, so we can calculate the mole fraction of each of the species in the product, and we can substitute those mole fractions back into the equilibrium expression in order to calculate the final composition of the product stream. And then we can also calculate the conversion of each of the species.